G'day all. At Mount Gravatt campus on Tuesday, we did get through the introduction to chemistry in the lecture. So Mount Gravatt guys, you don't need to watch this unless you would like to see a slightly different rendition of the same thing. But at the Gold Coast, we ended up spending a bit more time on some of the other discussions and the other points and didn't quite get to this. So this is a quick run through. I think I promised you 10 minutes. I'll try and make that work. So I might have a few less illustrations, but of just a quick introduction to chemical sciences as it appears in the junior secondary curriculum, Australian curriculum. So first up, really quickly, junior secondary syllabus, the Australian curriculum science, and I might talk about syllabus and curriculum as different issues later on as we go. But in the Australian curriculum science, for year 7, this is the only chemical science. There will be some physics, or physical science as they call it, some biology and some earth and space science, but this is the only chemistry topic that has to be taught in grade 7. Mixtures including solutions contain a combination of pure substances that can be separated using a range of techniques. And that was our lab this week, was separating mixtures using a range of techniques. And you both saw some techniques, but also used some, but not all. For year 8, it's properties of states of matter in terms of motion and arrangement of particles. So we played with some dry ice, which is solid state of matter going straight to gas state. We played with some liquid water. We can think about ice and we can think about steam. So we've got the different states of matter and particle model, which we're about to talk about in a minute. Differences between elements and compounds and mixtures can be described at the particle level. And chemical change involves substances reacting to form new substances. And we didn't really do that this week. Next week, we'll do more chemical reactions in the lab, where we're changing one substance into a different substance. Year 9, matter is made up of atoms, protons, neutrons, and electrons. Radioactivity happens in the nucleus. Chemical reactions involve rearranging atoms to form new substances. Mass isn't created or destroyed. And chemical reactions, including combustion and the reactions of acids. So those are some of the things that we look at, are important in living and non-living systems and involve energy. So things like fire, combustion, involve energy transfer, but basically all chemical reactions either emit or absorb energy. And there's a number of those that are biologically important, that we get our energy from the food and that gets turned into motion in our muscles, and that gets turned into heat and so on. So we'll get into that more as we go as well. Year 10, atomic structure and properties of the elements are used in the periodic table, which we'll talk about in a minute. And different types of chemical reactions are used to produce a range of products and can occur at different rates. So that hopefully is giving you a sense of what's in the syllabus. The big ideas of chemistry, I talked about the big ideas. I think the two big ideas are everything is made out of chemicals. Myself, the microphone, the camera, the lights that are shining on me, my glasses, everything, the air in the room, etc. Everything is chemicals. Chemicals aren't just those things on the first slide in the colourful liquids in the glass bottles in the laboratory. Everything, including the students themselves, are chemicals. And structures at the atomic level, the level of atoms and molecules, explain the properties we see at our level. So what's going on in the particle world is what explains the behaviour and the properties that we observe. So the particle model is incredibly powerful. Everything is made out of particles. They're very tiny. We can't see them even under a microscope. And they vibrate, connect, bond, move. They explain the states of matter, solid, liquid, and gas. And plasma, the state of matter that's in stars. And I'm not going to talk about that now for time reasons, but the plasma is the most common state of matter in the universe. Everything is made out of atoms with a nucleus. The nucleus is in the center. The nucleus contains protons, which have a positive charge, neutrons, which have a neutral charge, so no charge. And orbiting around the nucleus is, sorry, I use a mouse to drive it and it just slid down the lectern. That's what that weird noise was. Around the nucleus are orbiting negatively charged electrons. Now, positive charge, negative charge is attracted, but because they're in orbit, they don't fall down, like satellites around Earth are orbiting. It's more complicated than that. It's quantum, but we won't get into that in our course. Okay, that's about all you need at primary level about atoms and their structures, although we'll get into the periodic table a little bit. In the same chemical element, so a chemical element has particular properties. So gold is a chemical element, chlorine gas is a chemical element. Water is not a chemical element, it's a compound because it contains both hydrogen and oxygen. An element is just one thing unto itself. And every atom of gold has exactly the same number of protons in it. Every atom of hydrogen has the same number of protons. Every atom of sodium has the same number of protons, and so on. That's what makes it that element, is having the same number of protons. It can have different numbers of neutrons, and that's what makes it a different isotope, and that relates to radioactivity, which we saw is in the syllabus. But we'll get into that more when we talk about physics, really, because radioactivity is one of those things that's on the dividing line between chemistry and physics. In fact, one of the dividing lines we often use is that chemistry is about the electrons, physics is about the nucleus. So anyway, the curriculum document didn't quite use that dividing line. And the periodic table, the idea is that a guy called Dmitry Mendeleev, who's fascinating, look him up because I could tell you the story, but I haven't got time now, basically discovered that every 8 elements, you got an element with very similar properties. So as you counted up the increasing numbers of protons, every 8th element had these similarities of properties. And so he started creating a table. And it turns out that it's not actually every 8. It's got a relationship that we'll see in a moment, and it increases, and it's got to do with how the electrons are organized. But you can use the periodic table of elements. He used it to do things like predicting elements that hadn't been discovered yet. But we use it to understand the properties of the chemical elements. So here is the periodic table, or one representation of the periodic table. You can see that there's one row of 2, hydrogen and helium up the top, and then there's a row of 8. So it goes lithium, beryllium, and then there's a gap, and it goes boron, carbon, nitrogen, oxygen, fluorine. You don't need to memorize these element names, by the way. So there's a row of 8, another row of 8, and then there's a row of 18. And then there's a row of 18 plus 2, 4, 6, 8, 10, 12, 14, 18 plus 14, 32. So the rows get longer and longer because this row should fit in here. So it's a complicated thing to draw. We usually draw it like this. You could actually draw it as a series of linked cylinders, which would be more accurate but much more difficult to draw. Basically, this one is color-coded by things that have similar properties. So the orange ones down here are called the alkali metals. They have particular properties. They are very, very chemically reactive. They will explode if you put them in water. So you might have seen sodium in water or potassium in water. You could have a look on YouTube to have a look at that if you're interested in that. The darker orange ones over here, helium, neon, argon, krypton, xenon, radon, and yes, krypton is a real chemical element, are the noble gases or the inert gases. They don't chemically react at all. So you've got this column, very, very reactive, this column not reactive at all. And then the halogens here, fluorine, chlorine, bromine, iodine, are very reactive again. You've got some of the common ones we know, so carbon, nitrogen, and oxygen. Nitrogen and oxygen make up most of the atmosphere. Carbon dioxide in the atmosphere is a problem. Carbon monoxide in the atmosphere is even more of a problem because it's quite poisonous. Phosphorus, sulfur, etc. And then in the middle are the metals. So there are a bunch of metals in here. Silver, gold, copper, mercury, etc. are the metals that are in here. And the radioactive elements tend to be in this group here and along the bottom here. So the periodic table is just a way of organizing all of the elements, counting up from number 1, which has 1 proton in the hydrogen, number 2, 3 is lithium, where's my cursor gone? 3 is lithium, beryllium, 5 boron, 6 carbon, 7 nitrogen, 8 oxygen, etc. And we go up to, on this table, about 113. We can actually go up to about 118 now because we've discovered more elements than this table actually shows. But again, we'll get into this a little bit more as we go. But the periodic table is an incredibly powerful tool because it enables us to really understand the properties of elements in some systematic way rather than kind of randomly by just looking at individual elements by themselves. So that's about all I'm going to say about an introduction to chemistry. Certainly you can ask questions in the discussion board or by email or in class. There's lots of possibilities for further discussion, but I hope this has given you a quick, really quick overview of what we mean by chemistry and how we teach it in junior secondary. Thanks a lot. See ya.